What is the conservation of angular momentum? If there is zero net external torque on a rigid body, its angular momentum is conserved. If the body changes shape so that its moment of inertia changes, its angular velocity changes to keep the angular momentum constant. So, students and friends, stick around, watch, and learn. Question number 1. If the Earth's climate continues to warm, ice near the poles will melt, and the water will be added to the oceans. What effect will this have on the length of the day? Justify your answer. What's the answer? Neglecting effects of external torques, the Earth's angular momentum, L equals I multiplied by omega. This would remain constant. The melted ice would move from the poles towards the equator, away from the Earth's axis, and the Earth's moment of inertia would increase slightly. Hence, the angular speed would decrease slightly, and the day would be slightly longer. Again, the answer to the question, the day would be slightly longer. Question number 2. The outstretched hands and arms of a skater preparing for a spin can be considered a slender rod pivoting about an axis through its center. When the skater's hands and arms are brought in and wrapped around his body to execute the spin, the hands and arms can be considered a thin-walled, hollow cylinder. His hands and arms have a combined mass of 8.0 kg. When outstretched, they span 1.8 meters. When wrapped, they form a cylinder of radius 25 centimeters. The moment of inertia about the rotation axis of the remainder of his body is constant and equal to 0.40 kg squared. Question is, if his original angular speed is 0.40 revolutions per second, what is his final angular speed? Alright, for the solution to this question, if you look at the rough sketch that we have here, the outstretched hands and arms of the figure skater can be considered a slender rod, alright, with its axis at the center. The distance from the tip of his right hand, alright, to the tip of his left hand is said to be the same as the length of a slender rod, right? Now, when the skater's hands and arms are brought in and wrapped around his body, they're considered a thin-walled hollow cylinder, alright? So, based on this, okay, we will determine the moment of inertia of the figure skater, okay, initially when his hands and arms are still outstretched, all right? And that formula for the moment of inertia of a slender rod is equal to 1 over 12 multiplied by the mass and the square of the length. So when we substitute, All right, 1 over 12 times 8.0 kilogram, which is the combined mass of the arms and hands, the skater. All right, and the distance from the tip of his right hand to the tip of his left hand when they are outstretched, all right, is said to be 1.80 meters. That has to be squared. So doing our math, we will get the value of the moment of inertia of the figure skater, specifically the moment of inertia of his arms and hands still outstretched, and that is equal to 2.16 kilogram meter squared. Also, according to the problem, um, the moment of inertia, the moment of inertia of the remainder of his body, okay, his head, all right, his legs, his feet, the moment of inertia about the rotation axis, which is assumed to be the vertical axis, okay, is constant, and that is equal to 0.40 kilogram meters squared. So, in short, we have to get the total moment of inertia of the figure skater initially, all right, when he is in this position, okay, about to spin. His hands and arms are still outstretched, all right. So getting the total initial moment of inertia of the figure skater, that is equal to 2.56 kilogram meter squared. All right. So when his arms and hands are brought in and wrapped to his body, as shown in this second sketch, all right. In this position, the figure skater's body can be likened to a thin-walled hollow cylinder, all right, whose moment of inertia is equal to its mass times the square of its radius, all right. Substituting again the combined mass of his arms and hands, 8.0 kilogram, to be multiplied by the radius, 25 centimeters or 0.25 meters. So in this position, all right, the arms and hands of the skater can be likened to a thin-walled hollow cylinder whose radius is 25 centimeters, which in meter, of course, is 0.25 meters. All right, so you got to square it and then multiply it to the mass, 8.0 kilogram, and we will get the moment of inertia of his arms and hands when brought in or already wrapped to his body equal to 0.50 kilogram meter squared, so that we can get also the total moment of inertia of the figure skater, all right, when he is already in this position with his arms and hands already wrapped to his body. All right, we just add 0.50 kilogram meter squared plus 0.40 kilogram meter squared, and we will get the value of the total moment of inertia I sub 2 equal to 0.90 kilogram meter squared. So obviously, okay, from this initial position, all right, the moment of inertia of the figure skater is decreased, all right, from 2.56 kilogram meter squared, it's decreased to 0.90 kilogram meter squared when he changes the shape of his body, meaning from this position with his arms and hands still outstretched, all right. The moment he pulls his arms and hands to his body, all right, in this second position, okay, his total moment of inertia is now equal to 0.90 kilogram meter squared. So if you're going to compare the change, the two moments of inertia from 2.56 to 0.90, it's like the moment of inertia of the figure skater has decreased by almost 3 times, right? So, the second part of our solution is to apply now the law of conservation of angular momentum, which mathematically, okay, can be written this way. Okay, I sub 1 omega 1 is equal to I sub 2 omega 2, where the product I sub 1 omega 1 means that in this position, while his hands and arms are still outstretched, the moment, the angular momentum of the figure skater is just equal to his uh, moment of inertia, I sub 1, multiplied by his angular speed, omega 1. All right? And that product is known as his angular momentum, which according to the law of conservation of angular momentum, that has to be equal to the product of his moment of inertia, I sub 2, when he is already in this position, multiplied by his angular speed, omega 2, which is still to be determined. All right? So basically, this is what the law of conservation of angular momentum is telling us. All right? There is a what we call a constant value for the angular momentum initially. All right? The initial angular momentum is just equal to the final angular momentum. That is what is meant by this formula. All right? And since we are looking for omega 2, all right, we'll just isolate and come up with this working formula for omega 2, which is equal to the product of I sub 1, omega 1, divided by I sub 2, and substituting, all right, we have the initial moment of inertia of the figure skater earlier computed as 2.56 kilogram meter squared to be multiplied by his initial angular speed, 0.40 revolutions per second, okay, and then divided by his moment of inertia I sub 2, 0.90 kilogram meter squared. All right, doing our math, we will get the value for omega 2, or the angular speed of the figure skater when he's already in this what you call position. All right, with his hands and arms already wrapped to his body. So omega 2 is equal to 1.14 revolutions per second. All right. When this is compared to his initial angular speed, 0.40 revolution per second, all right, this comes out to be almost 3 times or 3.0 times greater. All right. So if um, the moment of inertia of the figure skater has decreased, okay, 3 times from 2.56 kilometers squared to 0.90 kilogram meters squared by changing his shape or body shape, all right, from this position with his arms and hands outstretched to that position where his arms and hands are brought in and wrapped to his body, okay, uh, the moment of inertia has been decreased almost 3 times, okay. According to the law of conservation of angular momentum, okay, a decrease in the moment of inertia corresponds to an increase in the angular speed. All right. So we came up with this computation for the angular speed, where we see that the angular speed of the figure skater has increased 3 times its original. All right. So the inverse uh, proportionality relationship between moment of inertia and angular speed is clearly illustrated in this problem. And that is essentially what the law of conservation of angular momentum is telling us. We're down to our last question, question number 3. A teenager is standing at the rim of a large, horizontal uniform wooden disc that can rotate freely about a vertical axis at its center, right? As shown in this rough sketch. The mass of the disc, expressed in kilogram, is denoted by capital M, and its radius in meters is denoted by capital R. The mass of the teenager, also in kilogram, is denoted by small letter m. The disc and the teenager are initially at rest. The teenager then throws a large rock that has a mass, also in kilogram, of small letter m subscript rock, or m rock. As it leaves the thrower's hand, the rock is traveling horizontally with speed v in meters per second relative to the Earth in a direction tangent to the rim of the disk. The teenager remains at rest relative to the disk, so rotates with it after throwing the rock. Question is, in terms of capital M, capital R, small m, and m of the rock, as well as the symbol for the tangential speed v. What is the angular speed of the disk? Treat the teenager as a point mass. So we'll have the solution to this question in just a short while. Here's our solution. We express the moment of inertia of the disk, labeled I sub d, and that is equal to 1/2 the mass times the square of its radius. Alright? So this is the moment of inertia of the disk. The moment of inertia of the particle, okay, we treat the teenager as a mass of a particle, or as a mass particle, and its moment of inertia I sub p is just equal to his mass, small letter m, multiplied by the same radius, capital R, square. When we combine them, all right, we have the combined moment of inertia of the disk and the teenager treated as particle mass. Okay, when these two are combined, we'll have big M divided by 2 plus small m quantity R squared. And our target variable is for us to determine the angular velocity or speed of the disk, all right, which also happens to be the angular speed of the teenager, right? So we just label it here as omega sub d and p. That's our target variable, all right? This is the angular speed of the disk with the teenager, okay. Together with the disk, the teenager will be rotating exactly after he throws the rock, all right? And the angular speed of the rock may be expressed as his tangential velocity v divided by the radius big R, which means that just after the rock was thrown by the teenager, okay, the rock will have a angular momentum labeled here as L sub rock being equal to his moment, the moment of inertia of the rock, which is mr squared multiplied by its angular velocity, okay, which when expressed in terms of the tangential speed, it will be v over r, right? So you will notice that we can simplify the equation for the angular momentum of the rock. We just cancel out the big R here, all right? That is, the angular momentum of the rock is just equal to its mass, small m, multiplied by its tangential speed or velocity v, multiplied by the radius capital R. The radius capital R is simply, uh, you have to refer to this sketch. That is the distance from the, what we call, from the rim of the disk, okay, uh, to the location of the axis. The axis is assumed to be a vertical axis. So that is labeled as big R, capital R. All right? Now, according to the law of conservation of angular momentum, the rock, just after it was thrown, this angular momentum of the rock is just equal also to the angular momentum of the disk together with the teenager, which is assumed as a particle mass. So L sub d and p is equal to the moment of inertia, which we earlier calculated here, all right, and its angular velocity, omega sub d and p, happens to be our target variable. So these two angular momenta are supposed to be equal according to the law of conservation of angular momentum. Because initially, all right, before the teenager threw the rock, okay, the disk, the teenager, including the rock, they were all at rest. In other words, the total angular momentum of the system is zero. All right. So for the total angular momentum after the rock has been thrown to be equal to zero, then it means that the angular momentum of the rock right after it was thrown must be equal to the angular momentum of the disk and the particle, all right, or the teenager. Hence this equation. So we can isolate now omega sub d plus p, which is our target variable, all right? So the angular velocity or speed of the disk with the teenager, all right, is just equal to the product of the moment of inertia of the rock times its angular speed divided by the moment of inertia, which we determined earlier as I sub 1, equal to big M divided by 2 plus small m quantity r squared. So substituting, right, the mass or the moment of inertia of the rock, okay, m of the rock times tangential speed v multiplied by big R to be divided by I sub 1, where I sub 1 is expressed as quantity big M divided by 2 plus small m quantity R squared. And simplifying, we get as our answer to this question, all right, we are asked to express the angular velocity or speed of the disk in terms of the big M, small m, big R, and small v. And the answer is, we have here the formula for omega or angular speed or velocity of the disk equal to mass of the rock multiplied by its linear or tangential velocity v, okay, divided by half of the mass of the disk plus the mass of the particle here, all right, is the mass of the teenager, small m, okay, times the radius big R. So this is our answer to the question. And we were able to determine this by, again, applying the law of conservation, all right, of angular momentum, which, when summarized, we have this concept. The total angular momentum of a system that includes a rigid body and a particle is just the sum of the angular momenta for the rigid body and for the particle. So that ends our video tutorial. Thank you very much, as usual, for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.